Groundwater resources are widely used for water supply, so monitoring and maintaining quality standards is essential to ensure water safety. They are under increasing pressure that can compromise their quality. In this lesson, we will take a closer look at the main factors that determine groundwater quality, as well as the methods and models used to study it. The main sources of pollution for aquifers are natural elements that can contaminate aquifers due to the presence of potentially toxic substances in the subsoil, such as arsenic, fluoride, and iron, agricultural activities, since they often use fertilizers and pesticides that can seep through the soil and contaminate aquifers, industrial activities, or urban infrastructure, such as sewage systems, whose leaks can contaminate aquifers, and saltwater intrusion, leading to salinization of groundwater in coastal aquifers. Contaminants can often come into contact with aquifers as a result of interaction with surface water flows, for example rivers, or through the infiltration of water into the soil. To support the management of water resources and decision-making processes, mathematical models and computational tools have been developed. Let's now look at some of the principles that guide the construction of these models. The mathematical modeling of processes can be based on a mass balance for a substance dissolved in water. Aquifers and soils can be described as porous media where water can flow through the spaces within a solid matrix. The fundamental processes that occur within individual pores at the micron scale are the flow of water, which contributes to the movement of contaminants by advection, molecular diffusion, which contributes to the mixing of a substance dissolved in a fluid, and chemical or biologically activated reactions that can induce transformations, such as the formation of new compounds, or influence the transport of a substance, for example by delaying it as in a case of adsorption. Problems related to groundwater quality involve spatial domains much larger than individual pores, so generally it is not possible to describe the entire problem explicitly. Therefore, it is necessary to use effective models, that is, models capable of representing the behavior of the system without describing all its details. For example, the fact that a fluid has to pass through a porous medium with a complex geometry causes a distortion of the concentration fields, facilitating the dilution, known as mixing, and the dispersion, known as spreading, of contaminants. These factors therefore need to be properly quantified with coefficients and parameters. The local distribution of concentration also determines the effectiveness or ineffectiveness of reactive processes, once these are considered on larger scales. Given the complexity of the physical system of interest, as well as its interactions with chemical and biological components, it is essential to consider the achievable objectives and the information that can support them when developing a modeling approach. It is essentially impossible to build a model capable of accurately representing every single aspect that can influence the quality of a groundwater system. Therefore, it is necessary to choose which aspects to focus on when building a model, considering those that are most important for the objective you want to achieve. When building an effective model, it is essential to start with a conceptual model that is suitable for representing the subsurface system of interest. This could involve, for example, the transport of contaminants through stratified or complex aquifer systems, as well as processes that occur in a vertical soil column or the flow induced by density differences in a coastal aquifer. The definition of a model must then take into account its formulation through a system of mathematical equations capable of providing a quantitative output. In the simplest cases, the mathematical system thus defined can be solved using an analytical solution, that is, in closed form. More frequently, it is necessary or possible to describe the architecture of the geological system and to explicitly consider nonlinear and coupled processes. In these cases, it becomes necessary to use numerical approximation through computational tools. There are software packages capable of providing a numerical approximation of the reactive transport of contaminants in subsurface media. In general, these can be based on a description of the space-time evolution of a concentration field and therefore use an Eulerian approach. On the other hand, it is possible to simulate the path of a sample of particles using a Lagrangian approach, which is then used to discretize the mass of a contaminant. Within reactive transport models, there are parameters that determine the importance of the individual processes involved. For example, hydraulic conductivity, dispersivity, and the reaction rates associated with chemical and biological transformation processes. A typical feature of subsurface systems is that they are not visible or accessible, which makes it necessary to use probabilistic approaches, that is, approaches capable of incorporating various sources of uncertainty. Considering this, the complexity of a model must be balanced with the measurements and information available. Parameter estimation methodologies can provide insight into the quality of a model and its ability to determine parameters under uncertainty. For example, contaminants of agricultural origin can percolate through the soil toward the aquifer and are subject to a wide range of chemical and physical processes. Probabilistic approaches can leverage prior knowledge about the phenomena involved in direct observations, thus helping to provide an estimate of environmental risk. In conclusion, we can say that the quality of groundwater systems depends on a multitude of factors, including the geological structure of the subsurface, climate, land use, and the socio-economic activities connected to them. Modeling is a fundamental tool for the conscious and sustainable management of this strategically important resource.